Happy day, friends. We're going to take a look at some DC circuits today and do a ranking of the voltage, also known as the potential difference, across a couple of points relative to ground in the circuit. So let's take a look at the circuits that we've got on tap today, and we'll see what we can come up with as we go through an analysis. All right, so I'm going to show you I'm going to show you 6 circuits, and the batteries are either voltage or double the voltage. Doesn't really matter what it is. You could consider it to be a 6 and a 12 or a 10 and a 20, whatever it is. One's voltage and one's double that voltage. All the resistors are going to have the same value, an ohm, 2 ohms, 3 ohms, whatever it is. They're all resistor R. Now, in order to simplify things, we're going to take any resistance in the wires and assume that we've already got it in the resistor R. Same thing with the battery. We're just going to say whatever the battery voltage is, that's the voltage. So we're going to ignore any extra resistances that might crop up. So anything internal to the battery, anything in the wires, we're going to assume we've already taken care of all those and they can be neglected. So our task here is to rank the voltage of the upper right corner of the circuit relative to the ground. And you can see I've labeled them with the letter here, A, B, C. And then we'll go down here and we'll see D, E, and F. Now, just to remind you of some of the symbology here, the batteries are the lines over on the left side here, and I've labeled the battery voltages. It's you can see it's either V or it's 2V. All right, so every circuit has the battery over on the left side. The negative side of the battery is connected directly to ground. That's what this symbol is here. I guess if I were to draw it exactly, it should be something like that. But you know, you get kind of lazy and all of a sudden that becomes it's one of something like, well, I try to make it near like that rather than a resistor, which is a little bit more well defined. Okay, so the ground is, we're going to define 0 volts to be this corner, the bottom left of each circuit. You'll see the ground is connected to the bottom left of each circuit. And there are different resistors. There's different amounts of resistors in the circuit when they're in different places, but their values are all the same. So our task is to try and rank the voltage that we find at these points relative to the ground on the lower left of the circuit. So how are we going to do this? The first question we might ask is, what's going to be what things are going to make the difference here? What things do we need to consider? Well, you can see that we have 2 different battery voltages, and we have not different resistor values, but different numbers of resistors. Now, what does that mean in total? It means the circuit resistance varies. So if you look at A here, there are 3 resistors in the A circuit and only 1 resistor in the B and 1 resistor in the C. So the total circuit resistance that the battery is aware of is different. Now the circuit will have different currents basically due to that different resistance, but the battery doesn't know anything about how many resistors there are. It doesn't know anything about where they are. It just knows there's a resistance it has to push on, and it does that. Now, if you make it up with one big huge resistor or a number of resistors or of differing or equal value, as long as the total value of the resistance is the same, then the battery will do the same thing. Doesn't matter. So let's take a look at how to rank this. How are we going to attack a problem like this? Well, we could do a couple of really easy things. We could just say, well, the ones with 2 V batteries, those are the winners. And they're going to rank all equally because they've got double voltage batteries. So C, D, and F are all equal, and they're all greater than A, B, and E. Is that the way to do this? What would be wrong with that? Maybe take a minute and figure out, if we look only at the voltages, what would be the problem with doing something like that? Well, if you thought of, well, wait a minute, there's going to be current flowing and the resistance in each circuit is different. Well, it's different amongst pairs, right? I mean, there's one resistor, but there's 3 over here and there's 2 over here. So they have different resistances. Therefore, we should probably consider what is the effect of these resistors on the voltages in the circuit. So a resistor is something that essentially takes the energy that the battery is putting into the circuit and uses it to do something. So at each one of these points where there's a resistor, energy is coming out, right? So there's going to be what? A voltage drop across the resistor if you're traveling with the current. So when you look at what the voltage is at the top right corner, we have to figure out, okay, what's the voltage of the battery? Let's figure out the drops in the voltages due to any resistors it's gone through, and then rank that according to the voltage compared to ground. Okay, so we'll start with 0 volts on the bottom left hand, and let's take circuit A as an example here. If I start down here at the ground and I'm a charge in the circuit, the first thing I'm going to do is go through the battery. You'll notice in each of these, the current is going to be going clockwise. The first thing I'm going to do as a charge is I'm going to go through the battery and I'm going to come out and I'm going to be energized, because that's what a battery does. It energizes charges. So it doesn't charge them, it energizes them. This is an energy source for this circuit. So the charge is going to then be, wow, I'm really energized, really energized, really energized. And then it's going to get to the first resistor and it's going to say, oh, the resistor is trying to do something, light bulb, say, or a clothes dryer. It's doing something. It's taking energy out of the circuit. So some of the energy is leaving here at resistor A. And by the time I get to to point A, I've lost some of the energy that the battery has given me. So how much do I have left? Okay, that's the key. That's the question here. All right. So what would be your thoughts as to how to attack something like this? Do we need to calculate everything and say, well, we've got a numerical analysis, assume the batteries are 6 and 12s and assume all the resistors are 2 ohms, and off you go? Do we need to calculate everything? I hope you say no. So let's take a look at how to conceptually attack something like this. Now, in this first circuit at point A, like we've discussed, some of the energy in the system will be lost. That corresponds to a voltage drop. The energy is, the voltage is the energy contained or possessed by each charge. So if I'm one charge and I'm moving around, I had suddenly lots of energy. I had energy V, right, coming out of the battery, and then I've lost some of it going through the first resistor. How much did we lose? Well, since each of the resistors is identical, what must be true about the voltage drops as the charge goes around the circuit? Is it going to lose suddenly a whole bunch in the first one? It's going to say, oh, I'm almost, that's it, I'm almost out. And then I'll just kind of trickle through the other 2 resistors and say, whew, barely made that one. No, we're going to talk about the charges losing equal amounts of energy at each resistor, because all the resistors are the same. So in this case of circuit A, there's going to be a 1/3 voltage drop across each of the resistors because there's 3 resistors. Yeah. So by the time the charge gets to point A, how much kind of voltage will the charges, how much energy will the charges be having at point A? They still should have 2/3 left. Okay, so we can really go through and look at, well, how much are they losing and how much is left, and then just rank that. We don't even need the V here. It just, I mean, it makes it a little bit more proper or precise, but really we're just ranking that fraction. All right, so I'm going to assume we know that there's going to be a V in each one of these expressions. I'm just saying, all right, first one's 2/3. Okay, take a look at well, yeah, let's take a look at B. So here a charge comes out of the V battery, and what does it do on the way there? It does absolutely nothing. So how much is left? Hasn't lost anything. So there should be still a whole one left. Now here at C, basically same thing's happening, right? But look at the voltage. How does that change things? There'll be 2 V's left, right? So we're going to go down here. So far, we've got 2/3 in A, we've got 1 in B, and we've got 2 in C. Go ahead and take a look at the other three. See if you can come up with, what do we have going on in D? What's happening in D? Take a look at D and see if you can come up with what the voltage of the charges at point D is. If you need to, go ahead and pause the video now. I'll move on with it. Okay, so if you look at circuit D, it's the same exact setup as A, except we've doubled the voltage of the battery. So therefore, each of these must still be losing the same amount, right? So if I think of double the voltage, well, there'll still be 2/3 of that double left over. Right? So we should have essentially 4/3 left here at D, because the 2-volt battery, as it goes through 3 resistors, it's going to lose 2/3, 2/3, and 2/3, as opposed to in circuit A where it lost 1/3, 1/3, and 1/3. So they have double the energy, and therefore they're going to lose double the energy through each resistor. So at D we should have 4/3. Okay, here's circuit E. This is a slightly different beast. It's only a 2-resistor circuit now. Pause the video and come up with an answer for E. What did you have here? This is a voltage V, 2 resistors in the circuit, half each, right? Okay, what do you have for point F? Double what you had for E. So we can make up with a ranking. What's really interesting here is if you look at the ranking, B and F are actually tied. And that's because I doubled the voltage, but I also doubled the resistance. And I set it up so that the loss of energy as in F, as the charges go through the first resistor, that equates to a full 1V loss. Right? So in this case, our total ranking should end up being something like, well, I'm looking at C as being the leader here. So it should be C greater than D, which is 1 1/3, which will be greater than B and F, which are tied. And that's going to be greater than, we got 2/3 and we've got 1/2 left. So we've got E and we've got, I said E, but I wrote A, and now we've got E. Okay, there we go. So that should be what we're looking at for a ranking. There certainly are many ways of doing these, as there are with many of the circuit problems. Thinking about the voltage drop involves kind of conceptually using Ohm's rule. Okay. It's thinking about, well, if the resistances are all the same, then the current that flows through them, since this is a series circuit, that current is all the same. And therefore, if I go across each one of these resistors with a voltmeter like this, and I test the voltage across each R, I should be getting the same number. This is the same idea as what's called a voltage divider. So when you have a series circuit like this, it divides the voltage up across each resistor. Now the trap here is what I was mentioning earlier. There's a tendency to think, well, there's 3 resistors and all the voltage shows up across the first one because that's the first one in the circuit, and then the other 2, as if they were light bulbs, the first one would be really bright, but then the second and third would not be very bright at all. And probably by the time you got to the third one, it's completely off. So the misconception of the charges giving up all their energy in the first resistor, they don't do that. They know there's more coming. They know when they get through there, I got to divide this up. Okay. So the thinking is not that anything's getting used up, but that it's going around and dividing equally in cases of series circuits. So I hope this has been helpful, and I look forward to seeing you in a future video. Ciao, folks.